here's how quick it is. What is this a graph of? In other words, what does it look like? It's a what? Which is called a... Yes, this is what I mean by study your notes. This was like the first thing we wrote. The second box, I think. Alright, so it wasn't the second box. It was this box. If you look and see that equation format, what is it? What's the graph going to be? Oh. It's a circle, okay? So it's different than this. What is this a graph of? Well, let me make it up. 4x plus 5. What kind of a graph is that? Well, slope isn't a thing, but it's not a... There is slope in this, but it's not a shape that we're graphing, is what I mean. That's a line, right? If I said this, 3x squared plus 2x plus 5, what is that going to graph to be? Well, that's what its name of this is, a quadratic, but what does it look like? Yeah, good. Parabola, like a U kind of, right? So this is a line, 4x plus 5 is like that. This is some kind of parabola. What if I did this? Absolute value of x, what does it look like? Okay, look at me. It's a V shape. Now, here's the point. In math, we ought to be able to look at a function rule and know its general form of the shape that it would graph to be, right? Like, is it a line? Is it a parabola? Is it a V kind of shape? Is it, if it's exponential, is it sort of taking off like an airplane or a jet? Or is it a circle like this one? Just by looking at the format. That's an important thing. You want to take Algebra 2. Like, that's what Algebra 2 is looking at functions and knowing how to graph them. And people hate it because, well, actually, I don't know why, but sometimes people hate it. But, like, here, graph every one of these based on what you know about the shape, like that kind of thing. You remember. Then you're looking at key features, domain, range, x and y intercepts. Where is this increasing, decreasing for all of these? And it's a big deal. And I know some of you haven't taken Algebra 2, but the ones I'm giving you, other than this one, actually, no, that one too. All of these are Algebra 1 graphs, actually. So it should be familiar. For us, when you see that, you got to think circle. In fact, we just did a problem today in calculus that it was an equation of a circle. And you just have to know, oh, that's a circle right away. What does this equation give us? This red one. So I hope that kind of previewed what you'll be doing a lot of, and then plus a lot more stuff. Make sure there's a lot of it. Guys, what does it tell us? So remember we said get your general form lined up with this one. It shouldn't be plus, it should be minus. X minus h squared plus y minus k squared equals r squared. Okay? And then we know, hopefully we can look at that and know everything we need to. So what are h and k? Yeah, it's the center. What are they in this problem? Nope. Read your notes. This is why I tell you to read them every night. Because if you don't, then you have to go learn it all over again every time.
Isn't the center?
We already said that.
Yeah.
I'm asking for the numbers. Like
Oh.
where is the center?
Uh,
I'm a 2 and 5.
She already said that. It's not 2 or 5.
Oh, -2, -5.
There we go. -2, -5. Why is it not positive?
X minus H.
Yeah, like the one we're given says plus, but it's supposed to be minus. So the only way to change that is to make this minus -2. Minus minus is plus. So it has to be minus negative in order for that to actually be a plus, right? For it to be correct. So you should have written in your notes that to find h and k, you write the opposite of what it looks like in the problem, right? So in this case, it looks positive, but you write negative, and vice versa. Okay, so our center is at -2, -5. Okay, what else can we get from the equation?
25.
Not in half, but you're on the right track. I would say it this way, equals 25. What can I write over here? Don't tell me the whole circle equation. Specifically, what equals 25?
5.
Well, I don't mean numbers. I meant concept.
Oh, the whole radius, or our whole diameter
Uh-uh.
of the circle.
No, but you're kind of thinking in the right way. Because the diameter is 2 radius, 2 times radius, right? No? Okay. I will do this if you say it's necessary, but let me ask you. Do we need to do one of these every single day for you to remember it? I mean, realistically, should we have to, is what I'm asking. So what are you going to do to fix this? Every day, right? I mean, we can take time to do one of these every day. Here's how this problem should go. Ready? Oh, hey, here's a graph. I see it's the graph of a circle. I know that because I've seen the circle equation in my notes about 60 times. I'm talking like I'm one of you. Okay, so I'm going to line up my equation with the given. I'm going to circle so it's lined up. So HK, I know it's the center because I've read that 60 times. I know this negative h is 2, so h must be -2. I know negative k is 5, so that means k, positive k, is -5. And I go plot my circle center. And then I look over here and I'm like, okay, that lines up. R squared is 25. So R is what? I know how to square root. So R is 5. Okay. Now we come over here and we can't do diagonal 5 because that's not the same length. So we just have to go 1, 2, 3, 4, and there's a 5. 1, 2, 3, 4, 5 for sure. Just here on the left and right, up and down ones. 4, 5. 1, 2, 3, 4, 5. And then we just do our best to connect. It's not going to be a perfect without a compass, right? So that was about a minute. And for these, if I don't give you graph paper, then you could still plot this, right? You could draw an XY axis. 1, 2, 1, 2, 3, 4, 5. Put a center, and then put some points like here and there, etc. Right? You can sketch it on graphic or on plane paper. So super easy. What's hard about it? Yeah, you got to read it to know it, right? You got to know it. The math, meaning the easy part, I mean, is there's nothing hard about what we did once you knew what you were looking at. And the only way to do that is to study. And this is one thing out of going to be probably 100 things by the end of the year. It's a big deal. Anybody want to do another one? Yeah, let's do. So get rid of all this. I think I'll just. I'll just cover that right one. You guys want to make one up?
X plus 4 squared plus y 7
Okay.
equals 42.
Nice. All right, graph that one, everybody. So we recognize that it's in the form of a circle. And let's maybe be specific as to why. Or what makes it the circle form. That's different. You know, a second ago I wrote several other equation versions. What was different about those than this? I can write them again. Something like 3x plus 2, 3x squared plus 2x plus 5. And then we did this one. Okay. True, they don't have parentheses.
Y equals
They have y equals. And what does this one have?
X and Y.
It's together, right? Okay, well, what is this kind of graph? Like, if we graphed it, what shape would it make? Huh? A square? Is that what you said? Okay. Good thought. It's not a square, but I can see kind of why you think that. This is also a line. In fact, we could rewrite this one to be like this first one. Not the same, but it would be like it. So that's called standard form. That's a line. So x and y are on the same side, but what's different about them? What's the power of the x and y on this one? It's 1. What's the power of the x and y on this one? Squared. It's 2. So if you have x and y on the same side and it's squared, you're thinking circle, right? If you just have x squared, then you're thinking parabola. And if you just have x and the power is 1, then you're thinking line, okay? Anyway, so when I look at this, I see x and y on the same side but squared, so that's probably a circle, right? We have other shapes like an ellipse that kind of have a similar format, so it's not always a circle, but at least it tells you it's not one of these other ones, right? Like another common one. So we get x minus h, okay. X minus h squared, y minus k squared equals r squared. Okay, and then we start circling. So where's our center?
-4, +7.
Yeah, -4, +7. So I'll go put that on here. -4, not +4. -4, 7. Right there. Okay, and then how do we deal with that? Yeah, r squared, radius squared, which is not the diameter. The radius times 2 is the diameter. So, like Bailey said, we square root to get the radius. And because we're graphing, we kind of need to know what that is roughly, right? It doesn't have to be perfect, but it can't be a simplified radical because that's not helpful to graph. So this is roughly 6.5. And for our graphing purposes, 6.5 would be fine. So I'm just going to turn this into roughly 6.5. Okay, so from here we go down 6.5. Well, from 7 down 6 is to the 1, and then to the half. Okay, from negative 4 over 6 and a half is to 2 and a half. And then left 6 and a half will be off my paper by just a little, probably not quite that much. Okay, and then on mine, up 6 and a half would be 13 and a half. So, it's not a great circle, but it does, yeah. Here, let me draw it in there with this. Now, I should have done it on the last one because it was actually on the graph, but that's okay. So set the pointy part on your center, set the writing part on one of your points, and then just spin it around. Check that out, I hit that one pretty good. Now we gotta find 3 dots that are impossible to see. They're on here somewhere.
You were just on them.
I was?
Yeah, you were. Just keep clicking on where the degrees are.
Oh, there they are. See, good grief. Alright. How'd that one go? Is it better?
Yeah.
Okay. I mean, do you feel like compared to this problem that we did yesterday, this should be an easy points problem, the circle one, right? Good. With that said, let's review tangents. So if you have that example in your notes. Remember, a tangent is a line that touches the circle only once, at only one point that we call the point of tangency. And then we wrote this theorem that a tangent is perpendicular to any radius. So any tangent and radius combo form a right angle at the point of tangency. And then we were able to solve for lengths because of that using the Pythagorean theorem and some good algebra. So big idea, make sure you get the 90 in the right place and then set up, you can zoom in on the triangle if you want to. I didn't write that in here, but you certainly can. Use the Pythagorean theorem and solve for x, in this case expanding carefully. So we did that one in our notes. We also saw this is starting to be a good chance to look at each radius in a problem is always going to be the same size. And that some of these are going to have to add together, and that's why we had x plus 18. And then we came back after we did that example and did that one. Whoop. Where'd it go? I can't look at the arrows and, there it is, and at the board at the same time. So we did both of these, but I'm focused mainly on B for now. Okay, so that time we had 2 of these lengths where it was in parentheses, an x plus something. So we had to expand and get 2 of these trinomials to combine carefully, right? Alright. Does that all kind of ring a bell from yesterday? Part A, remember we were just checking if it is actually tangent by proving that it's a 90-degree angle. So we did that in 2 ways. This one we just had to subtract for the angle. And then the one that we did earlier yesterday, we had to actually plug into the Pythagorean theorem and make sure that the sides were equal for a right triangle. But they weren't, so that was not. Alright, that should get you caught up. And I'm sorry I'm flashing around a bunch, but let's try this one. It says line M is tangent and line N is tangent to the circle T. What is the value of x? So you don't have to use Pythagorean theorem for this one, I'm going to tell you that, but You do have to draw on some prior knowledge from the quadrilateral unit. That's my hint. Quadrilaterals. Okay, here's the hint. You're looking at this shape. Index, and this is an angle problem. Like I said, there's no Pythagorean theorem or anything. It's purely angles. So, give you another minute or so. Alright, so we're focused in on this shape. You guys remember the name of it? That's a kite. Good job. And we're told this angle is 135 degrees. Trying to find that angle. How? Well, obviously that's not enough information unless we know something else, which we do. Okay. Good. So line M and line N are tangent, which tells us what, Linda? Well, this is, yeah. Is that what you're saying? Okay, so line M is tangent to radius BT. Line N is tangent to radius CT. So that means we can plug those in as 90. Now, how do you find X?
Just add 135, 90, and both are 90s, and then subtract it from the 60,
Awesome.
which will give you 45.
Okay, so basically, remember in a quadrilateral it's 360 degrees like a circle. So we know three angles, we just subtract those from 360 to get that last angle. But the big piece of information that you had to know is tangent and radius are perpendicular. So thank you, Linda. And Bailey, good job, guys. Alright, that was a review of yesterday, wasn't it? Tangent, radius is perpendicular. Everybody say it. Tangent and radius are perpendicular. Okay. Alright, let's try one of these. I'm not going to read it, so you can try doing that. Getting your problem set up, and then I'll come in and give you a hint if you need to in a minute. I'm not cutting you off, just verifying that you have your picture labeled like this. Or you could use X, you don't have to use R. So here's what you should be looking at. So we have our right triangle. Again, when you draw a figure outside of the one given, I think it's helpful to draw it in the same position, same orientation. Okay, so we don't know R, and this is R plus 7, and that's 11. And of course this is a right triangle, why? Yep, good. Tangent radius, right? So what are we going to use to solve for R? What tool? Yeah. So we'll do R squared plus 11 squared equals R plus 7, that whole thing squared. Okay, this one, remember, is R plus 7 times itself. And so we'll get R squared plus 7R plus 7R plus 49, and then combine your two 7s. Okay, now what?
Yeah.
These cancel, they're on opposite sides of the equal sign and they're the same. So this is how that would look if we showed it. Subtract R squared from both sides and now both of them are gone. Okay, now what?
Subtract 49 from 121.
Okay, so minus 49 from both sides. So is that 72?
Yeah. And
Okay.
then,
Go ahead.
divide 14 by both sides.
Good. And 72 divided by 14. It's 5.1. Does this tell us? Yeah, it doesn't say anything about how to round, so 5.1 is good. All right, how'd that go? Good, good, good. Okay. Good, good. Okay. All right, that is tangent to the radius, tangent radius relationship. Let's write another one down in your notes. We're only going to do 2 for tangents. So this will be another one to study tonight. And we're going to call this tangents from the same point. And of course we'll draw a picture. Guys, what does that mean? Well, let's this time draw the picture first. So I want you to put some point out here. And draw tangents that connect to that point on either side of the circle. Okay. And let's go ahead and put in a radius to each one. That is a weird circle. Or center. Okay, what's true about the angle right there on that radius? It is 90. And if you want, you can put R. I think the more times we see that see radiuses in the circle, the better off we're at seeing it when we're doing problems. Okay. All right. Let me ask you this: those 2 red lines. What do you think we're about to write that's true about them in this box? Looking at it. They what? Well, they're tangent. We'll say that they're tangent. So yes, they'll touch the circle at one point. Any other thoughts? Like, what does your gut tell you is true about them?
They always have 90.
What?
They always have 90.
Here they will. That was this theorem. Remember, a tangent to a circle is always 90 at the radius.
If you were to like cut it in half, like split it down the middle, both sides would be equal.
Okay. What were you going to say?
They're equal distance.
They're the same length, yeah. Equal distance. And then I like where you're going with this. So just watch for a second. Don't try to write and keep up. This is what Bailey said. We connect that line from center to the point. You guys remember triangle congruence? Again, don't write, just kind of watch. Remember we had side, 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 angle, side, angle, angle, side, and we had a hypotenuse leg. Remember those? Turns out these 2 triangles are congruent, which means the 2 red lines are congruent. But which one of these makes those triangles congruent? And I'll remind you that this blue line is reflexive congruence. Trying to think if we can make a case for that. It is side angle side if these 2 angles are congruent, but we don't know that for sure. So let's take that one. We currently only know one angle.
HL.
It is HL.
Oh, because it's reflexive, so it's...
Yep, and that's the blue line is the hypotenuse for the triangle, and then the two green lines are both radiuses, right? So it's HL congruence. And remember CPCTC? So if these two triangles are exactly the same, don't the two red lines also have to be exactly the same? So that's where this comes from. Okay, it's good to know that. Okay, so let's go write the theorem. Again, we'll write it more in a text, like just a sentence. So if two lines are tangent to a circle, and then here's the key part now, like we in the last one we had a key part which was to the radius. In fact, I probably should have underlined it. This key point is from the same point. So if two lines are tangent to a circle from the same point, that's the key piece. They are congruent. You guys remember the symbol for congruence? Like a cake with frosting.
No.
Hayden said she would make us a 5-layer cake.
Do you want us to draw the line in the middle now? Or do you want to just keep it blank on here?
No. The big idea is to do this. And we're to mark that those two are congruent. So you don't have to draw the blue line.
Okay.
In fact, I might even take mine out because I want you, when you go look at this, I want you to focus on the red lines being congruent. But it is good to know that it's hypotenuse leg. So, hypotenuse leg congruence. That's just a side point. Okay, so what is this going to allow us to do, do you suppose? You know, when we did tangent radius, we set up right triangles and used a lot of Pythagorean theorem. What about this? It's still a right triangle, right? It's just in a different spot. In fact, I just erased the right triangle. So there's one. Still a right triangle. And then so is the other one. Some of these problems are a little intimidating looking when you first look at them. And then you're like, oh wait, it's actually pretty easy. Okay? So let me show you what I mean. Now, by the way, that word proof, that was what we just talked through, was HL. Okay? So, do you guys miss proofs?
No.
What? You're not going to be sad if we don't do any?
Nope.
Nope. Do we have any?
Huh?
Will we have to do any more?
No. Okay, so here's an example of what I mean. Doesn't that look kind of intimidating? Okay. It's actually not bad at all. And I'll show you what I mean. But let's do a couple things before we get there. So looking at this one, you don't need to write this one. Well, I don't know if you do. I shouldn't tell you that. So it says Tx is 12. And Tz is 20. It says, what are xz and yz? So these two. First of all, what is true about xz and yz?
They're congruent.
How do you know that right away?
Because it's split down the middle.
That part doesn't actually matter.
Oh, they both have corresponding side lengths and equal angles on both sides. They're both the exact same.
True. You're making this
That was
too
a
hard.
terrible way to explain that.
No, but you're right. It's just that you're overcomplicating it. isn't Z a common point for both of those tangents?
Mm-hmm.
How do we know they're tangents? Because this time it doesn't say they are. Yeah, it's showing right here. Radius and line is a 90th tangent, right? And these are tangents from the same point. So Bailey's kind of like reproving that, which is good knowledge to have. But we don't actually need to, because we know we have the theorem that says tangents from a common point are congruent. So we can immediately just say those are congruent. Okay? So once we know one, we know both. But how do we find it? Whichever one, like how do we find one or the other? Go ahead, Silvana. I'm going to draw a hint. So the first person who sees it, say. That's not exactly. Guys, we're trying to find a length. Right triangle, Pythagorean theorem, right? Good. Where else can you put the 12? In the circle picture. Why? It's a radius also. Good. Okay, why don't you set that up real quick and solve it? Do you find it weird that circles have a lot of triangles in them? So this is almost another triangle unit. It's just that all the relationships come from circle stuff. Okay. Did you get 16?
Mm-hmm.
Awesome. Good job. Okay, so guys, keep looking. When you're dealing with lengths, keep looking for the Pythagorean theorem. We did see in the segment, the area of a segment, that we had to use trig. But I think more commonly you use Pythagorean theorem. Any questions on that one? Okay. All right, let's go look at this one. And I think you'll find it better than what it looks. I don't want you to try to write it, I just want you to watch. And well, not watch, but do it with me. But our goal is to find the perimeter of, what does this mean? Yeah, well, the whole thing, though.
The whole area?
It's not an area, it's a perimeter. Of the quadrilateral. You guys see a quadrilateral? You don't want to leave right now. This thing is what we're trying to find the perimeter. We talked about perimeter. What does perimeter mean? What does it mean? Peri means what? No. That was the periscope, but the periscope part we talked about was this part.
All around?
It means around, the distance around, right? Meter is a word for measurement. So what do we really need? Well, we have parts of it, but we need some parts that are missing, like this CD and AB, right? Rather than take it in whole chunks, here's how you do these. It's actually pretty easy. Do you see how D is a common point for these two tangents? So what can you do with the 6? 6. Okay? And then we come over here to C. C is a common point for these two tangents, so what can you do with the 3?
So it's basically the same other side.
Right? And then 7 can be copied there. And 2, and this is kind of busy with all these little lines, but that's okay. 2 gets copied there. And then how do you find the perimeter? Yep. So I'm going to start at B and go 2 plus 2 plus 3 plus 3 plus 6 plus 6 plus 7 plus 7. Okay? Now, sometimes the way a problem is given, it might, let's finish this and then I'll show you so I can erase. 4 plus 6 is 10, plus 12 is 22, plus 14 is 36. Okay, that's all. See how it's easier than it looks? Okay, let's see if I have one. Yeah. Maybe. Radius is 12. Actually, that's probably more than I want to do just yet. So let me go back and show you something that could happen on these. Here's another version. Let's say I tell you that AD is 10. Let's make it bigger. 31. So this is just a twist on what we just did. So if AD is 31, we still have to go around and copy everything. But does 31 get copied anywhere? No, because it's the whole length. So what would you copy in order to complete this?
31 minus 6.
Yeah, right? This little A to the tangent point is 31 minus 6. Right there, which is 25. Okay, and then where can you copy 25?
On the other
Okay, and then the rest of them are the same. So you might have to do something like that a couple times. Like if I scratched off the 3 and said that BC is 20, well now 20 minus 2 is 18, right? And might have to do that a couple times as you go around. But it's the same otherwise. So don't be intimidated by those. They're actually not too bad. So